Gabriele Fadini is going to present his work that he carried on during his PhD. I met Gabriele in person during my secondment at LAAS in Toulouse. And yeah, so he is a PhD student under the supervision of Thomas. Okay, Philippe Sourel. Yeah, and then he also did the secondment in no. Okay, in DFK Bremen. Yeah. So yeah, enjoy.
So thank you, Julia, for the presentation. I would also like, the IIT and the organization, Gabriele Pucci, for the opportunity of presenting my work, and for you to be here just to attend to my presentation. I was very happy to know that also at IIT there are a lot of people working on co-design, because especially working on this topic for my PhD, I found that it was quite challenging. And I feel that it's good that there is some kind of build-up of community that is going on, many different locations, many places. And I'm very happy of sharing, some of the findings and the methods that developed during time. So as Julia was saying, yes, I'm supervised by Thomas Frayol and Philippe Souer, and I've carried on my PhD, the PETO team, LAAS. I've also been collaborating with Andrea Del Prete, which some of you may know, has some ties with IIT, apparently. And so, yeah, I will present some of the results that I had in these years, particular with this Codesign and legged robots. So, as you said, I'm right now, and my background actually is quite, let's say, mixed, because I started my work as a mechanical engineer, and then I decided to move in mechatronics, and now I'm working in robotics. And this is something that tells a lot about the co-design approach, because really it's trying to put together a lot of different knowledge bases and methods. I think it's one of the main strengths of this approach that allows us to really synthesize smart designs for performing some tasks. It's really the core of the approach that we're trying to translate in robotics. I've also tried to do a little state of the art about co-design and robotics. And what we find is that so co-design has been used and developed for a lot of different problems, and just recently it's been trying to attack a problem as complex as the problem of leg locomotion, which is really tied with the hardware that we want to optimize. Because as you know, for sure, like the systems are very, very complex to control and design at the same time, because have to face a lot of difficulties related to the fact that they're under-actuated, that we are missing some knowledge in terms of the perfect model of the system that is not possible to achieve. So we have to use this is increasing the sim to real gap due to the nonlinearities, and also in terms of complexity, the system have a pretty high number of degrees of freedom. So they really they really presented a big challenge to just simply to control or to design, trying to do let's say, to exploit the relationship between the two things. It's pretty complex. So it's an hard problem, but it also enable us to really exploit the platform at best. In particular, for what we can achieve in terms of task following, and also to increase the energy efficiency and possible robustness, which are two of the, let's say, goals that we tried to address during my. What we see often in robots is that there are some waves of the implementations that implement good designs. For instance, in the case of humanoids, we see that the successful robots like Digit, Atlas have dynamics that are allowing for a simple control, like Digit, pretty close to a linear inverted pendulum model, presenting some other complexity, but moreover, more or less, it's easy to stabilize with simplified models. And also in the case of Atlas, simple models work pretty well. Or there are also some other trends pretty interesting in the frame of quadrupeds that have been developed and used extensively, come from optics, showing how the proprioceptive design of the actuators, simplifying control for achieving. This has been, say, implemented at first with successful quadrupeds like from MIT, from the work of done by Kim and Patrick Wensing, and then has been ported to a lot of different platforms, one of which is Solo, which is the robot that we have been working on and my research stemmed from. Robot here to represent a fully open design that we can have access to a very low level, and this is enabling us to modify some parts pretty, as we know, we have the complete knowledge of the system. So the main question is, since we see that there is this kind of trends that implement, that allow us to have a lower access to the hardware and to really tap most of the performance, we wonder if it's possible to automatize this process in a way so that we can select the hardware that is allowing us to better achieve the task and to minimize high level goals. So we see this patterns, which lightweight systems with inertia concentrated or high power density actuators there. But we also know that from the engineering point of view, selection problem is very complicated because the design decision space is have a lot of possible choices, even if you have to select some motors from off-shelves catalogs. There is a problem that goes complexity that is combinatorial, and moreover, it's difficult to predict what the impact of the choice will be on the final design. So what we've been trying to work on is some tools or some methods that can ease this conception designing phase that can be used maybe by system designers or roboticists. So we have some high-level idea about the task that a platform should do, but we really want to be sure that it will be the best version that can be deployed. And we can do this with by using some nominal design, so what I would call a good idea, and then by exploiting some technologies that are already there, so design, optimization, and simulation. Workhorses for roboticists. This process has to be integrated in the same kind of framework. Codesign by itself presents itself as a pretty complex problem in which we are trying to minimize something, and the main way that we write this kind of problem, especially for the robotic systems, is through an optimal control problem in which we specify some evolution, some dynamic, some high-level constraints, which actuators, control and state of the robot, and we try to minimize some metrics. See that, I mean, this problem of minimizing at the same time state, control, and design parameters that I've been calling with this letter D becomes a classical OCP problem in which we're just trying to minimize, optimize state and control once we fix some the instance of design. So when the design related parameters are, and by using this idea, what we've been exploiting is a bi-level approach in which there is an exploration phase for the design parameters and an optimization phase for the trajectory. So with this in mind, the problem, which was pretty involved and required some specialized technique, can be solved with standard tools. What I mean by this is that it's automatically split in two parts. One that is mostly taking care of selection of the hardware, so the parameters that have been called, and the following task, which is just trying to optimize a given formulation that we have been proposing. We're using two loops, what we call the outer loop, that is selecting the hardware through a genetic algorithm, and the inner loop is just minimizing the trajectories for a given robot model that is being out of a population of initialized. For each individual of this population, from the genetic algorithm, after that trajectory optimization is done, we have as an output the optimal trajectories and also the minimized cost, which in our case mostly related to the energy consumption. So with this information, we can feed back the minimized cost to the genetic algorithm, and then the genetic algorithm can understand in a way what designs are performing better for the given task. And with this information, the genetic algorithm that we've been choosing is CMAS. So can decide how to evolve the population of to explore the region that is performing the best. This cycle repeats over and over until a terminal condition is met, convergence or a maximum number. By itself, I mean, this sounds rather simple in the outer loop, but is also motivated by the fact that adding these additional variables really bring a lot of complexity to the problem. So using this kind of randomized exploration is necessary to not be affected by local minima problems, since this problem is even more complicated than the standard OCP. So in the work, we've been working on open hardware from the Open Dynamic Robotic Initiative for a considerable amount of research. This is a project that has been carried on at Bank under the Felix Griminger and Ludovic Righetti. The idea was to develop hardware of completely known current level for the researcher. That the actuators and the characteristics of the structure are known. Moreover, the idea is that the actuator blocks can easily be purposed for different robot topologies. Here, I'm presenting the quadruped version of Solo, and the biped version that is called Bolt. But also some other variants are there, like it's possible to build some manipulator systems or something by the robots of the hardware. And the core of the work was to understand, since we have this really accessible system that is pretty versatile in design, that can be purposed freely, to understand how to use the same hardware technology, right? Same motor types, which in this case is from the drones, to make the robot more useful. So to understand also the scale of the robot was impacting the performance of the system, taking into account the power efficiency. This was particularly important, I mean, to have a model that is estimating the consumption. Because one of the issues of having quasi-direct drive is related to the torque density, and the fact that they generate a lot of has to be managed. So to obtain a platform that for a given task is minimizing electrical losses, it's quite important. And we thought that the idea was pretty interesting. It was not something that the designer can do from an initial standpoint. You really have to bring the trajectory optimization. So one main part of the work was to understand actuator model, identify it, and determine how it's being modified by the selection of the motor and the transmission system. So here you see the opened the open actuator model that is Polo and some other robots. As you may say, is simple. And the main idea that we had was to understand how Coulomb friction, coefficient, are being modified by the selection of the motors and the transmission. So in a first part, we work on this side. Then another part that is related to the hardware is about the structural scaling. And there are a lot of different ways to modify the scale of a robot. What we suggested initially was to the material the same and also the same of the structure, but to tie the section scaling of the length so that we can keep some kind of structural rigidity. It is important to have a structure that, which may be problematic in the case of technologies like what concerns the energy efficiency. Once we found out how all the parameters related to the friction problem and for the OCP, the main idea was that some kind of interaction with the environment, which is given basically by a friction dynamics, we can reconstruct the power that the motor is being acquiring, because this one will be also related to the losses that we have in the transmission. Basically, for producing this interaction torque here at the joint level, knowing the transmission properties, we can reconstruct the total motor torque. So in the total, including the friction component that is up. And with this idea, we can also understand how much torque, how much power is being lost in at the joint level, and how much is being lost also in no losses, electromechanical point of view from the motor point. So we found that we could use simplified version of column friction plus the viscous term, so a pretty simple law, and solve the OCP taking into account these two components plus the mechanical. So in terms of the overall variables that I've been presenting, there is this size variable that is modifying the model inertia and length. And in particular, we've been using Nokia for parts, so size is really impacting the robot model that is being OCP. Then another variable that is related to the gear ratio. This is another variable from which we estimate the characteristics, the losses in identification of the actuator, so damping. And this also is impacting the torque limits of the actuator. So if we fix a motor and given gear ratio, we also have a maximum point torque that we can apply, and this is important as to count the limits of the OCP. And then here it's related, another variable that is mainly related to the motor choice. So initially, since we knew all the information about the motors that are used, made a simple regression from the set of motors those that we use was enough to identify mostly of the properties that are of interest to us. So that means the rotor inertia, the static torque that the motor can provide, the maximum angular velocity of the motor, and motor constant for the Joule dissipation. So this was enough. I mean, the idea was to use simply the masses of the motors and apply all of these properties. Also, another approach is possible, and that one related to discrete variables. So the motor selected as an integer from an integer set. This is also something that this will mean that from the selection, all of these parameters don't really need parameterization with respect to the mass, but are given directly from the off-the-shelf values. So this is everything that is impacting problem from the hardware point of view. Then from the control point of view, they've been saying we are focusing on the optimal trajectories, so state and control, and we try to minimize the cost function. But additionally, so other than the optimal trajectories that I've been in third versions, values, also been optimizing for robustness some controller-related parameter that allows us to scale up the Riccati gains from the DDP. So for view doesn't, I mean, not with DDP, the trajectory optimization that we loop crocodile, and one of the outputs of DDP, the optimal trajectories plus some gains that allows us to recorrect locally trajectory with respect to a state perturbation. So with this idea, if we have the optimal control U star and the state X star, and we want to follow the trajectory, and we have some kind of with respect to the actual state and the state that we plan to be, we can utilize this simple linear feedback to stabilize the plan. So the idea was to optimize with scaling factor some variables related just to the still the greatest part of the back done by the recutting game, but it's possible to add variables in the controller project. Then additionally, what we're doing also to add some additional variables related to contact timing by the outer. Basically, generate a different CP problem in which the contact phases are decided the outer loop. Optimization, we've been working on different kind of hardware. So in particular, some goals were first shown for a simplified version of the leg system, which is actually a leg which has an under-actuated base that can slide. And this is a simple test bed that allows us to understand the effect of the contact dynamics and the energy efficiency of the actuator. Then for robustness, also some work was done for serial manipulator similar structure. Then recently, also working on quadruped in collaboration with the FKI. And the quadruped itself was made find MJBot's open source platform. And the idea was to understand how, also in this case, the link shape, the link scaling, selection of the motor is impacting the performance. And in this work, a major focus was on periodic task, and this motivated us to change also the optimization framework lower level, so in the because version, not possible to include high-level constraints from initial, which is important in the case of periodic task in which we want maybe just to translate forward of a given delta at all of the other variables equal to the initial. And from this, I can maybe show you. And we were able to realize that, I mean, to validate the power cost function model with this prototype implementation. That was also quite interesting. And that identified the model for the losses and how losses was close to reality. So the idea was, I was saying, to start with a simplified robot. So the quadruped is different with respect to what we have on dynamic robotic initiative from the point of view of the mechanics, the materials. So we had to change stuff. The main ideas was to optimize the platform with off-shelf motors. And this was making the problem mixed integer. And we wanted to optimize also the scaling of the itself. Yes, and we also wanted to do that by taking into account the cyclicity of the constraints. And the idea was to use the same kind of structure, just replacing for the trajectory optimization part, yeah, Crocodile by Azadi in tandem with, and by solving the problems coming from the genetic optimizer with a computational cluster. So really exploiting in the possibility of parallelizing the problem. And as in the things that I've been showing before, what we really feed back to the outer loop is about the power consumption of the platform. As in this case, we can really enforce cyclicity constraints and additional task and dynamics related to so, I mean, this work really was more versatile in a way because it was could express a problem that was more rich. And we've been working on these new things that was related to the tries to cope with one of the problems of the standard OCP, which is related to the overall horizon that we can have in a cyclic trajectory. We have an estimation of the performance really for the operation life of the quadruped. So the model itself also was simplified a bit because we started from the 3D model and we used the version. Because what we really were interested to understand was also some kind of orthogonality in the motion in the, say, horizontal direction and the vertical one. Also, the two tasks that we wanted to optimize for were presenting this kind of orthogonality. The fact that quadruped has different planes. Yeah, here is related to the OCP itself. Have a whole body problem in which we optimize state the control, but also contact forces, acceleration. Yeah, some slack variables that we had to introduce in gamma. And there are additional constraints. Cyclicity. Then in the cost function, the running cost, there's nothing more than this main contribution that is related to the overall electrical power. In the case of the cyclic trajectories that we are optimizing, are a bounding gate, horizontal plane, and a backflip. Don't really need to add the mechanical energy because this depends on the state. And with respect to the translation of the base, it won't change because we're starting the trajectory kinetic energy, and the potential energy is the same. So in this specific case, it was enough to have a friction. So at first, we optimized this kind of bounding motion of the quadruped, and then we were able to test it on real hardware to validate the actuator model and the power consumption model. So in this part, since we didn't have gains from the OCP, it's not a TDP anymore, some tuning had to be done. So there is a simple controller on the joint position and velocity. But still, the results were pretty good from the identification point of view. Found that works were really close to the ideal ones. And for the initial part in which we are feeding forward term. And the same is also in the case of the electrical power consumed by the platform. It's probably mainly because we have mostly losses due to the Joule effect. Have a good estimation. So here, see the estimated values by the model, and measured one from platform there, just averaging the given sampling time, product current times battery side. Then we try to perform the optimization given this trajectory optimization problem. In this case, we focused on saying the scales of the link and the discrete off-shelf motor selection. So once we have a motor selection, we're interested in the ratio that, as I see from the motor types, is already integrated in the structure, and to the mass that we are adding to the system, because those motors are quite bulky. We cannot really neglect the mass, and the fact that we have a rotor inertia that is and some electromechanical properties that we have to use. So this is at least the model of the hardware. This is related to the actuators that we use. Then with this bounding, perform the optimization, evaluating a large number of individuals, and as you can see from the cost convergence seen by the outer loop, we reach some stationary values. It's here, and the different motor combination that we can explore. So in this case, it's just the optimization of leg, the planar leg. So we had a total of 4 possible combinations. See this kind of bands that are related. But more or less, we reach some stationary values. Then, yeah, saying we are really exploiting a large number of quadrupeds, and we're really optimizing everything, not avoiding to express a priori knowledge about the trajectory. So the trajectory that are being explored are quite rich. Then an additional optimization was done just for the motion, nominal hardware, and then in Codesign. This is just the task that followed, so dynamic motion on vertical plane. Also in this case, we were able to find optimal hardware. Found that the hardware optimized for the task was quite different. And this was expected, but because there is some kind of orthogonality in producing motion that have to go forward and motion that have to really exploit at best the angular momentum and positiveness in the vertical direction. So based on this, we also try to understand what is the trade-off between the two. We explored for the 4 different motor combinations landscape of cost, of the electrical cost, and from these values, extracted the Pareto front, motivate the design for the next. So based on the landscape that I did before and the nominal, we selected that now is being performed still at the FKI in terms of validation. What we would be happy to find is the optimized hardware is really minimizing energy losses of the system, and also if additional work is being following the optimal trajectory. So, as I would say, this Codesign approach is pretty versatile because we can optimize for a lot of different problems. And in the latest version, robust, and the evaluation of the cost can be validated. Then, on top of that, we were able also to optimize different tasks, extending a little bit of trade-off that we have on the hardware. then to go back to the saying, we find hardware that is a lot more energy efficient, and we can include pretty interesting information from other point of view about the robustness or the work on robustness. What we doing was related to simulating a lot of perturbed version of the same task with the recapitulation and understanding how the selection of the hardware was performing in terms of the linear local feedback all following. Then in the latest work, variables. Well, as I would say, this framework can easily address problems. Have possibly more tasks with parallelization, but there are some other related to application side, in particular the hardware itself. In the projects that I've been showing, the hardware is coming from a nominal robot, so a nominal from the open source project that can come. Some kind of expert knowledge is there. It's pretty. It would be pretty interesting to understand how this step can be automatized when possible by the robot generation. And then related to the just generation of the behavior, solving the right OCP problem is taking a lot of expertise. In some cases, it's even pretty brittle, fragile, not robust enough to be explored to a lot of different problems. So I would wonder if it's possible to, in a way, automatize also this part to be more general or to obtain more insight on the problem. Then, I mean, also by itself, right now is a tool that can be used for research. But it would be also interesting how it can be extended to test cases. I think that there are a lot. Just a matter of fact that approach is quite new and they are not there yet with probably kind of readiness level about that. So yeah, that was it. I mean, that was just to present what I've been doing so far, and I would be happy to discuss more if you want.
So yeah, thank you for the presentation. I don't know if you have any question also from the cloud. Just open your mic and ask the question. Yes. Okay, so thanks for the presentation. So my question is if the choice of using genetic algorithm was not the first choice you did, the first slide, or because before, for example, we started gradient-based method. Then what we observed was that we were struggling a lot to handle discrete variables. And then we switched to genetic algorithms. And now we are investigating other gradient-free methods. I don't know if you get different questions.
Yeah, I mean, it was an initial investigation. Like, that first, some of the problems related to wanted to explore like and develop a lot of other perform at one of the files I think.
Somehow similar, so we was to optimize geometries. Just like we started with some gradient base, but when we were working just with mathematics was still okay.
Another thing for me went for the fact that you don't really to optimize a lot. Properly select the hardware variables, have a space that is quite small for algorithm. And yeah, depends a lot also on the
Something on this.
your DOs, and you need to.
I think they cannot hear.
No? Yeah, maybe you can unmute yourself if you want to ask.
Okay, so any other question from the? Oh, okay. Question actually about the computational time, because our problem is in both cases, because we want to optimize okay the other parameters, but also I'm assuming you want to optimize the trajectory. It's not just the kinematics, but so how much time do you need for finding the solution, and then how dirty is the job that you have to do? Tune the parameter, tune the.
Oh yeah, the job is as I was saying. Ah, okay. Sorry. So yeah, the problem is huge, especially the last one. I also think that the cyclicity constraint is adding an extra burden. This is user perspective. It's not really mathematically based, because at the end you have this nonlinear like problem which shouldn't be impacted that much, especially if you use. But yeah, so in that case particularly, the problem was solved between, depending on the hardware, a pretty high level of accuracy, but also of kind of dispersion of computation time. This is something that, well, the fastest problem maybe solved in 30 seconds. The one that took the most time maybe solved in 10. So overall, what we did was to solve the problems on a computation cluster. that thing allowed us to solve the tasks in a reasonable amount of time, so roughly 10 hours overall. So, yeah, still is a pretty big yeah issue. Let's say could be sped up. I didn't really, so I tuned the parameters to make it efficient, but I guess that it can even made more efficient on that sense. But as always, there is a trade-off between the two things. So maybe you want to change the problem, and maybe you want to test a lot of stuff. That in that case, you decide to sacrifice the speed.
Thanks for the talk. I have a question. So basically, you evaluated using trajectory, right? And but do you solve a single trajectory optimization problem? So you consider a single task, consider like a neighborhood scenario.
In that case, I just fix a task. It depends on the problem. What I've been playing a little bit was also to modify the problem timings itself. That meant the number of nodes that were associated to contacts and line phase for the monoped, and that is also possible. I didn't do it for the quadruped, so as you were saying, the motion was kind of fixed in terms of displace, in terms of contact times. So all the timings were fixed in that case. But it can be potentially also something that is optimized. And in that case, I would do it in IP-opt. So the problem was that in the case of the monoped, I was using Crocodile, and Crocodile is pretty fragile. You cannot really optimize the timing inside the OCP, or at least from what I know.
I was more referring to the characteristic of the task. For example, if you were optimizing the backflip, and I don't know, some 8, or did you also change the parameter backflip task that you
I can play a little bit with that, but I didn't specify anything in between. So in that case, it was just the final state must be the initial state plus the rotation. So there is really a rotation of the. But yeah, you can do it for sure. You can impose some kind of inequality constraint on your final state. So you are choosing a given range of possible landing configurations.
Okay, so thank you for your presentation. And I was wondering how big was the sim-to-real gap once you tried the optimized models?
So it requires some tuning. And what we have, I didn't perform this specific part, but it was done at FKI, and it was in selection of a simple PD plus. So it was enough close to the hardware to be replayed with the optimal trajectory with feedback. So you have the joint position velocity and the optimal torque. They were able to follow it just with that. So I think it's pretty small.
Yeah, because I've seen you have implemented prediction model. So I was wondering if the computational effort was.
But still, yeah, I mean, if you really break it down and you expand it, this friction cost function is similar to what we have as regularization usually. So that you have a component that is quadratic regularization with respect to the torque, another one quadratic with respect to the velocities of the joints. So it's not really that much. You have an additional component that is probably the torque times velocities. Usually that thing is not important to have. That's, I don't think it's really impacting that much.
Carlotta, are you still there? Or?
Yeah, I'm here. Sorry for before. Ciao, guys. Sorry for before, but it was quite difficult from the cloud to hear only the answer part. But since you start talking, no, don't worry. Since you start talking closer to the microphone, everything went fine. So thank you, first of all, for the presentation. It was really interesting. And I was wondering about the search space covering, meaning that, as you said before at the very beginning of the presentation, when you deal with hardware optimization, basically there are a lot of combinations to be taken into account. And sometimes, in my experience, at least with the genetic algorithm, it's quite difficult to be sure that you're analyzing the most of the combinations. So I was wondering whether did you do some tests? I mean, do you have some evidence? Did you check the diversity of the population or some specific settings that allows you to be sure that, let me say, the covering was enough? I don't know whether I was clear.
Yeah, I understand. So in my case, the problems were not that big, so I could see how the evolution was proceeding on the design parameter space. And the other thing that I was checking was the convergence out of that. If the two things were good, so if I was covering well enough the design parameter space, and the convergence was going in the good direction, then I would say, I would say that the optimization was going well. I didn't perform additional checks, as you were saying. Maybe you can discuss more. I don't know.
Yeah. I will come back later to IIT, so we can also discuss face-to-face about it. Thank you very much. Thanks.
Welcome.
Other question? Okay, so can hear. Thanks to the speaker again.
Thank you.
Gabriele.